Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video for you. All math-based, of course, and it is an honor and a privilege to serve you today. I'm going to teach you a thing or two about some math, so how about it? Step into my virtual classroom. Let's have some fun. Today's thing is really more focused for my class. They have a test coming up, and it's a review on the first two modules for the year. It has to do with solving for equations, solving for inequalities, setting up equations and defining variables, solving proportions, evaluating expressions with order of operations, combining like terms, distribution, and substitution. So all those things come into play. So if this is something that pertains to you, that's great. You wouldn't have this worksheet necessarily, but what I have for you here is scanned directly from the source. You know, kind of like that water commercial, like directly from the source. So that's what I have here for you. So if you have this worksheet with me, great, awesome. I can attach the PDF for you if you want to get a printout of it for yourself. Otherwise, go ahead and take a look right at this with me. This is what I'm going to be writing on. I'll give all the examples here. Normally, I like to do a lot more of the why something happens. For the sake of time, I want to try and make it a little bit more just of the how. I'm going to try, how do you do it? How do you solve it? I might bring stuff up and how you process it, but not a lot of other knee-deep information. Okay, so let's go ahead and dive right into it. Now you're going to see some things with standards right here, or learning targets, success criteria. I might gloss over them just for the sake of the problems. Read those on your own. See if you are able to identify with what's happening here. But these problems, or these standards portions, contain these problems right here. All right, now if you do have trouble, by the way, if you have trouble finding a problem, if you have trouble with a certain problem and not this entire thing, and you want a certain problem to look for, look below the video here, look in the description section, and I'm going to provide timestamps for each and every particular problem, so you can fast forward straight to that. If you're on a laptop, you can click on the link. If you're on a smartphone, you might have to drag all the way with the time slider to that spot. But I have several problems. I think I have about 30 problems to do with you. So that being said, let's get to it. All right. So starting with number one here. Number one says, Miguel hires a plumber to fix a sink. The plumber charges $80 each hour he works and $30 for the parts needed to fix the sink. The following expressions models the charges by the plumber. So here's the model. This is an expression here and says, all right, this has to do with what Miguel's doing there. All right, how many terms are there? Now, a term is separated, or they are items in an expression that are separated by a plus or a minus. This plus divides the term 80x and the term 30 right here. There are two total terms. That is part A. Part B, what is the variable of the first term? The variable is the item that can change in the first term. It's modified based on what you substitute. That is this x right here. The x is the variable. You're used to hearing variables as those letters that we can substitute something and it's going to change. 80 can't change. 80 is 80. That does something different. In the context of the problem, what does x represent? You don't want to say a variable because we're talking about context. Now in the context here, it's not about Miguel. It's more about what Miguel might pay the plumber based on the services, but 80 represents the dollars per hour that he's going to charge. Now you can assume or make sense of the fact that the plumber might work 1 hour or 7 hours, and based on that he would charge more or less. So when you think of the fact that, okay, let's say he worked for 3 hours, well, $80 for the first hour, $80 for the second hour, and if I had a third hand, $80 for the third hour, 80 plus 80 plus 80, not so much about what is that number, but how else can you write 80 plus 80 plus 80? That's 80 times 3. You're multiplying 80 by the number of hours that you're working there, if that's how it happened. There's a plus 30, but the point that I'm talking about is this first term, the 80x. X is representing something that's multiplying with the dollars per hour, and this is a unit of time. X represents the number of hours the plumber works. That way, the plumber will make a certain amount of money based on how many hours he works. And in essence, well, actually, I'll talk about for part E. Part D, in the context of the problem, what does the first term represent? Okay, so I sort of just talked about this before. The first term, I'm going to go ahead and put in blue again. The first term, 80x, is 80 times x. 80 is the dollars per hour, X is the number of hours. So what happens when you multiply them? Let's try that 3 example again. 80 times 3 gives you 240. 240 what? $80 per hour times 3 hours, $240. That's how much money that the plumber is going to make for his hours worked. Not his total services, because the 30 is a part of it, but 80 times X. 80 times, the 240 was an example. 80 times X is the amount of money in dollars. The dollars earned, dollars the plumber earns, by X hours worked. If the plumber works 10 hours, that's a big plumbing job. If the plumber works 10 hours, he would make $800 for the hours worked. For the hours worked. Okay. Now, in the context of the problem, what does the second term represent? What's this 30 all about? The 30, let's take a look at the problem again. $30 for the parts needed to fix the sink. So, okay, he works 10 hours or 1 hour or however many hours, maybe half an hour. He still needs to order the parts to fix the sink, or needs to make sure he has the supplies. That's like an upfront cost. He says, okay, I'm going to work $80 per hour, but I'm going to charge you $30 for the parts. Doesn't matter how many hours he works, he's going to charge $30 regardless of what that is. It's kind of an upfront cost. And I don't know if that's the exact answer that any other teacher might want me to put, but it is an upfront cost. Remember, it's a constant value. 30 is just a constant number. It's an upfront cost for the services. So when you consider the total, how much are you going to pay this plumber? You're going to pay him an upfront cost of $30 plus $80 per hour for the amount of hours worked. Total, that would be something. So if he works 10 hours, 80 times 10 is 800, plus 30 is 830. He's not going to fix a sink for 10 hours. That is not a very good plumber, I'd say. All right. So that's problem number 1. All right. Let's go ahead and move on to number 2. Number 2, the perimeter of the rectangle is 86 inches. Use the picture below to write an equation for the perimeter of the rectangle. Notice it does not ask you to solve. All right. So in order for this to work, the drawing kind of helps us a little bit because it gives us measurements for width and length or base and height or whatever you want to say. But also it kind of helps establish that a rectangle has 4 sides. And this also helps as well. Opposite sides of a rectangle are equal. Next semester you might say they're congruent. But x plus 8, if this portion of a rectangle is x plus 8, then so is the left portion right here. If the top portion is 2x plus 5, then the bottom portion is 2x plus 5. That's the first bit, understanding what a rectangle is. The second bit is understanding what perimeter is. And perimeter is the surrounding length of your object, or as you might say, add up all the sides. Okay, so we could take all the widths and lengths and add them up together. What's really nice about this, and I want to associate this in kind of a different way, I'll show you, is that because 2 items are the same length on top and bottom as they are on left and right, instead of writing something like x plus 8 plus x plus 8, because there are 2 of them, I could say, for example, I have 2 multiples of x plus 8. Okay, it's just like the 80 plus 80. 80 plus 80 is 2 times 80. So x plus 8 plus x plus 8 is 2 times x plus 8. Plus, there are 2 multiples of x plus 5 as well. I can write 2 times 2x plus 5. Now you can write x plus 8 plus x plus 8 plus 2x plus 5 plus 2x plus 5. Remember, I'm adding up all the sides to represent the perimeter. This would equal, I'm not going to say p because we haven't defined p and because we have a perimeter of 86 right here. It's going to be just that, equals 86. That's all the room I kind of have for the problem, so that's all I'm going to write. You're not asked to solve, but if you were, we could distribute and simplify and try and isolate x in order to figure out what x represents and furthermore, what these parts are. You're not asked that though, so we're not going to do that. So there is a setup, a version of a setup for this problem right here. It's one that I very much accept and encourage that you try and write if possible. Problem number 3. Arwen pays $45 for a new video game. Each skin he buys for his champion in the game costs him $1.50 for his champion? Avatar? I don't know. He spent $63 total. Define a variable for the number of skins he buys and write an equation that models the situation. So you're not certain what a skin is. It's just an outer layer of whatever is applied. His champion, whatever the video game is. DLC, downloaded content. Here we go. All right, define a variable for the number of skins he buys and write an equation that models the situation. So kind of like this problem right here. This one was an expression. You can tell that X happened to represent something, and we could use the other numbers to make sense of what happened. The $30 was an upfront cost for the plumber's services. We knew that no matter how many hours he worked, we were still going to be charging the he was going to be charging the $30 regardless. Same with this. No matter how many skins Arwen buys, he is going to be paying $45 for that video game. So 45 is this upfront cost, this non-changing constant. He will be paying $45 somewhere. I'm just going to go and stick a 45 here. It's not going to multiply with anything, but it's going to be adding this dollar amount with other dollar amounts as we go through the rest of the problem. Now notice 45 is in dollars, okay? $1.50, that would mean $1.5, just so you're aware. If I write 1.5, I think I'll do 1.50. But if I write 1.5 for somewhere, note that you have to make sure that you keep the units aligned. If this is in dollars, then my next one's going to have to refer to dollars. But $1.50 is how many dollars per skin. Each skin costs $1.50. So what if he bought 10 skins? You would take the cost of each skin times the number of skins. We don't know how many skins he paid for. And that's where our variable comes into play. So when you're being asked to define a variable here, what they want you to do, or us, for the number of skins he buys, that's what you're going to do. I'm going to do X. I don't want to do S because S can look like a 5 and I already have a 5 here. So I'm going to do X represents number of skins. You're lucky we told you what we want you to define the variable as. X equals number of skins Arwen purchases. Arwen buys. All right, so if we take the number of skins he buys and multiply it by the cost of each skin, you'll get the total amount of dollars that he pays for all of those skins. When you add that with the upfront cost of the video game, it looks like that totals to $63. So what does the whole equation look like then? Okay, so $45 upfront cost. Now he's going to pay $1.50 for every skin he buys. Did he buy one skin? I don't know yet. We don't know the answer yet. I know that's not the answer, but what do we do here? We multiply this cost by the number of skins. Total, this is going to amount to $63. So here we go. That is your equation that you would set up. $45 for the video game plus $1.50 per skin times the number of skins is a total of $63. We do not solve this equation as per what is being asked. That's number 3. Number 4, Erin has an advertising business. She has $2,000 to pay for a fancy dinner for her clients. She will pay $600 to rent a place for the event and $35 per person for food. Define a variable for the number of people she can have at the event and write an inequality that models the situation. Now, the previous problems were equations because the idea is they matched up to an exact amount that we were going to be paying for. In this case, I think what we're saying is she has $2,000 that she's able to pay, but she might not amount to exactly $2,000. It matters how many people come, but what we probably want to figure out in this thing is it says define a variable for the number of people she can have. She can limit the number of people she can have, but she could also have less. So the question is, how many people could she have without overspending the 200? That's what the inequality is all about. So, in other words, we have to take all of her expenditures, the $600 for renting a place for the event and the $35 per person, and make sure that you can spend enough $35s, but not too many to exceed the $2,000. So this is a lot like the previous problem we just did with Arwen. There's an upfront cost of $600. I'm going to note that one first. She rents the place for $600. She reserved it. Even if she cancels the party, oh crap, I still have to pay the $600. So she's paying that regardless of how many people show up. All right? Keep that in mind. $600 happening there. Now, when it says defining the variable, again, we kind of do it for you. But it says define a variable for the number of people she can have at the event. This time I'm going to use the letter P. P is going to be the number of people attending event. All right. We don't know how many people it is, and really the idea is it can be any number of people from 0 to a certain amount to make sure she doesn't maximize the $2,000 spent. $600 here. We're going to combine that with $35 per person times the number of people that show up. Remember, if 10 people show up, that's 600 plus 35 times 10, 600 plus 350. We don't know how many people show up, so we use P, number of people that attend. So 35 times P. Now, on the other side of this equation, this is being compared to $2,000. So this is a certain amount of money that Aaron is going to be spending. On the other side of the inequality right here is $2,000. We have to make sure, and I'm going to go and write this, this is what Aaron spends. This is the amount of money she's going to spend. This is what Aaron has. We want to make sure that what Aaron has, that what Aaron spends does not exceed what Aaron has, meaning it can match it, but it cannot go over, which means it can either equal it or be under it. We also call that less than or equal to. What Aaron spends must be less than or equal to what Aaron has. She has $2,000. We have to make sure that what she spends is less than or equal to $2,000. We are not solving for this one. This ends up being the final answer right here. And we go ahead and we move on. But note how the wording describes everything that we're going to be doing here. By the way, the $35 per person, I guess, was for food. Great. All right, next page. Here we go. A lot of learning target success criteria, standards, and such. We're going to go ahead and go for numbers 5, 6, and 7. Solve. Solve for what? Find out what the variable should be in order to make the left side equal the right side. All right, depending on what class you're in, it can be talked about in several different ways. Maybe I'll express one in one way and one in the other way here. For number 5, I have n in the denominator. When I solve for n, it's got to be in a numerator. Point blank, I'm just going to say that straight up. So before anything else, I'm just going to go and tell you guys, if n is being divided on a side in the equation, you got to multiply both sides by n. We cannot allow n to be in the denominator in this equation. Now, you do n divided by n right here, you get 1, so it's gone on this side. But when I'm looking on this side over here, I have n times 6 over 7. I'm going to also write it as 6/7 n. If that helps you out a little bit, that equals 5. All right, now 6 over 7 is a coefficient that is in front of the variable, and we have to solve for it as it multiplies by that variable there. Now, if you have a fraction, it might seem a little bit different on how you can get it by itself, because you might say, yeah, when you multiply by something, we divide by the fraction, both sides. But dividing by a fraction is kind of picky to say. So it's easier to say, let's multiply by the fraction's reciprocal. 7 over 6, you flip it, we do that on both sides, and what happens on this side at least is the 7 over 7 becomes 1, 6 over 6 becomes 1, and now you have a variable here, n, with a coefficient of 1, and ideally you solve for this thing. We just got to clean up what's on this side. Now 5 is dividing by 1 right here as well. 5 times 7 is 35, 1 times 6 is 6, so we have now n equals 35 over 6. This cannot reduce. I'm going to leave it improper. That's fine. That's one way you could solve for it. There's another approach that involves kind of the idea of what I even say in my class, cross multiplication. It's a way of getting your fractions out of the way. I'll go ahead and do it with this problem. I'll do 2 ways with number 6, and I'll show you what we can do. Okay, number 6, 5 over 3 equals y over 9. There are several ways you can do this, but let's do the algebraic based approaches. The first one I want to say is that because y is in the numerator, all that y is doing right now is dividing by 9. So you could say, okay, if I multiply both sides by 9 right here, I've gotten y by itself. So you're already done if you do it that way, sort of. In this case, y would equal 9 times 5 is 45. So 45 over 3, which does reduce to 15. There's your answer. You're finished. But I promised that I would show the cross multiplication method as well. So outside of using that method that we just did, we could say, okay, to get rid of the fractions completely, let's go ahead and take the 3 and multiply it by y, and take the 9 and multiply it by 5. Ideally, what's happening is I'm multiplying both sides by 9 and both sides by 3, and things cancel like the ends did here. So what you have here after you cross multiply, 3 times y is there, 9 times 5 is on the other side, 3y equals 45, divide both sides by 3, you get right back to where you were here. So more steps than the previous problem. Could have cross multiplied here, that would have worked out, but you should get those answers regardless. N equals 35 over 6, y equals 15. Okay, number 7, we have a two-step equation. This is not a proportion this time, and we have to solve for x, and x is multiplying by 6 and subtracting 4. We must get x by itself, so we're going to apply inverse operations here to isolate it. 4 is being subtracted from 6x, so let's add 4 to both sides in order to start to isolate x. Negative 4 plus 4 is 0, so we just have 6x left on the left expression, and on the right expression, 26 plus 4 becomes 30. 6 times a number is 30. I think you guys know what that answer is, but in order to utilize this properly, we divide both sides by 6, and we're going to go ahead and get x equals 5. Now you can verify any one of your answers if you have the time and luxury of being able to do so. If x equals 5, that means I could substitute 5 back into this equation right here, and then the left side should equal the right side. 6 times 5 is 30. 30 minus 4 is 26. 26 equals 26. It works out. By the way, there's going to be another problem set later where they're asking you to describe what steps were being used for each thing. So let me break this down for numbers 5, 6, and 7 very quickly here. I'm not going to write them out. I'll just say them, and then we'll do them for future problems. On number 5, it looks like what I did was I multiplied both sides by n. What I used, when you do both sides, it's for balance. And when you do that, that's called a property of equality. And because I multiplied, it's something called the multiplication property of equality. So for number 5, that first step I did was the multiplication property of equality, multiplied on both sides. That's kind of what we're doing for almost all of them. When I multiplied both sides by 7/6, 7/6 is multiplied by that fraction, that's the multiplication property of equality as well. For number 6, cross multiplication, I'm not going to say it that way. Let's just say I multiplied both sides by 9 here, multiplication property of equality. Then, well, this one's simplified. So that was it. This isn't division property of equality right here because it's already dividing. I'm not doing it on both sides. I'm just dividing that straight up. On this one, though, if you were from here and you had to divide both sides by 3 to get to that step, that's called the division property of equality. Okay. Number 7, I added 4 to both sides, again for balance. That's called the addition property of equality, keeping balance by adding. And then I use the division property of equality right here. So that'll be used in a future problem, maybe on one of the next 2 pages. So I'll just go ahead and keep going. Numbers 8 through 11, we must solve. Okay. Now it's going to be the same as number 7 really, but the difference is we have a lot of simplification to do before we can get the variable by itself. So what I'm really going to do is I'm going to simplify each side, each expression first before I move anything over to the other sides. And simplification involves distribution and combining like terms. So right here, I have this whole y business all inside this quantity that's multiplied by really a -3. So if I distribute the -3 into both terms right here, I'm going to have a 5. And -3 times 2y is -6y. So that's minus 6y. And remember, this is still a -3. -3 times -6 is positive 18. So when you distribute, you multiply the item outside of the quantity by every element inside the quantity, noting the signs that are there. And this was a -3 for both items. Make sure you carry that sign through. This all equals -1. I'm still not going to move items over just yet because I have some like terms to combine. 5 can add with 18, and 5 plus 18 gives me 23. So I have 23 right here, and this is minus 6y equals -1. Okay. I haven't yet done any properties of equality. I'm just simplifying. I distributed, and then I combined like terms. Now what's left is to get y by itself, and admittedly I wrote this kind of bigger than I should have, so I'm going to shrink this a little bit. Okay. So, okay, here we go. 23 minus 6y equals negative 1. To get y by itself, let's go ahead and start with that 23. Move it over to the other side. Because it's positive, I'm going to start saying these words. I'm going to use the subtraction property of equality. Subtract 23 from both sides here. And we got 0 here. Do not ignore this negative that's in front of 6y. That is still a negative 6y equals negative 1 minus 23. I'm going larger negative. This becomes negative 24. Negative 6 times a number equals negative 24. In order to do this, I must use the division property of equality, divide both sides by the same value. I'm not just going to do 6 because I want to make sure that I have a positive 1 coefficient in front of y. I have to make sure that it's negative. A negative divided by negative gives me a positive. Negative 6 divided by negative 6 cancels out to be positive 1. Negative 24 divided by negative 6 is positive 4. Y equals positive 4. You may verify that for yourself. I want to move on. Okay. Number 9, x divided by 7 plus 9 equals 6. X divides by 7, 9 is added thereafter. Let's take care of the constant 9 first. Apply the inverse operation of addition, which is subtraction. I'm going to use the subtraction property of equality and subtract 9 from both sides. And my result now, 9 minus 9 is 0. I have x over 7 on the left side. 6 minus 9 is going to give me negative 3. Small minus large, I'm in negative territory. It's like 9 minus 6, but negative. Numbers dividing by 7 to get negative 3. What was that number? Let's go ahead and use the inverse of division, which is multiplication. I was about to write the answer there. Let's use the multiplication property of equality. Multiply 7 on both sides. 7 over 7 is 1, and so I have 1x on this side. Negative 3 times 7 is negative 21, and that is my result. Negative 21 divided by 7 is negative 3. That seems to work out. And that's it. Double check on your own, please. Okay, number 10. 6x minus 2 equals 4x plus 18. My goal is to get x's all on one side of an equation. I have x's on both sides right now, so I have to start working. These sides are already simplified. 6x minus 2 can't combine to become anything smaller. Neither can 4x plus 18. So let's go ahead and start to isolate the x terms. Let's move all the x terms to one side, all the constants to the other. If you don't mind, I'm going to color code this, but I'm going to do it all in one step. I think it's better that I put the x's on the left side here. Left side. I could put them on the right side, but it leaves me with negative x's, so I'm not gonna. I'm going to go and subtract 4x from both sides. Subtraction property of equality is allowing me to go ahead and do that. 4x minus 4x is 0 here. So that allows me to combine these on this side and have only x's on one side of the equation. In green, I'm going to go ahead and move this constant over this negative 2. If I'm moving x's over to the left, I want my constants over on the right. So I'm going to go ahead, minus 2 here. Let's go and add 2 to both sides. The addition property of equality is occurring right here. Negative 2 plus 2 is 0. So you can see what happens now. I have 6x minus 4x on this side that combines to 2x. And on this side, I have 18 plus 2, which combines to 20. And that's all that remains. Normally, you can do these in 2 steps. I just decided to do both steps in one. Sake of time, practice, acknowledgement that you can do it. Divide both sides by 2. Using the division property of equality, 20 divided by 2 becomes 10. So we get x equals 10. Notice I didn't write it that time. I'm trying to see how much you can pick up as I go along. Okay, number 11, let's go ahead and solve for n. Now n, there are 2 terms with n on this side. I'd rather simplify the terms first before I go ahead and ultimately solve. So I have 5n minus 2n. And notice that I pointed to this minus here and not this one. This minus has nothing to do with the 5n or the 2n. That's negative 13. But 5n minus 2n. Those can combine to give me 3n. And I still have the minus 13 right there. And this all equals 8. Okay, so let's start to isolate the n term right here. I have a negative 13 on this side, so I'm going to use the addition property of equality. I'm going to add 13 to both sides without writing it. See if you can do that. Add 13, it's gone here, and all I have left is 3n. Add 13 to this side, 8 plus 13 gives me 21. So 21 equals 3 times n. I'm going to switch these around. I like to put my variable on the left side. That's kind of a personal preference thing. I like to say that n equals something and not something equals n. This is totally allowed. Just switching it around. Divide both sides by 3, division property of equality, and you get 21 divided by 3, which gives you 7. N equals 7 is the final solution here. And again, by solution, what I mean is, when you substitute 7 back into the original equation, the left side should equal the right side, and it should pan out. I'm not going to do it, but if you have time on your test, when you're doing something like that, definitely go ahead and check that solution. This is my third video I'm recording today, and I've taught all day as well, so I'm kind of losing the voice already, so bear with me here. All right, number 12. Does each equation have no solution, one solution, or infinitely many solutions? Write the correct number of solutions in the blank next to each equation. You may want to try to solve each equation beforehand to help you decide. Okay, now what we've seen so far are all of these equations that have one solution. N only equals, this is the only thing I can substitute for n to make the left side equal the right side. This is the only thing I can substitute for y. Y equals, x equals. One solution in all of these. What makes something have one solution versus none or infinitely many? Let's go ahead and work through the problems first so you can get a scenario and what happens. And I promise that I'm going to do the right math to make it work. So that way, once we simplified it down, we'll say, what changed in all these things? And I'll let you know right now, each of these occurs at least once in each of these problems, at least if we set it up correctly. Okay, so for part A, 6x minus 3 times the quantity 2x plus 5 equals negative 15. Let's go ahead and distribute the negative 3, remember it is negative, into both elements of the quantity. So I have 6x, negative 3 times 2x is negative 6x. Negative 3 times 5 is negative 15. And this equals negative 15. I want to simplify this side first before I move things over. 6x minus 6x, that actually gives me 0x, right? And 0 times anything is 0. So these kind of cancel each other out. They're kind of gone right here. So all I have left in this equation is just negative 15 equals negative 15. If you'd like, you could add 15 to both sides, but then you'll have it say 0 equals 0. Basically, we have something where something equals the other side. Kind of weird. I didn't make a mistake, but something happened there. I'm going to hold that for a second and go on to part B, or problem B. Problem B, negative 2x plus 3 equals 5x plus 4 minus 7x. All right, the left side is simplified. I can't combine like terms there. It's all done. On this side, I have a 5x minus 7x that I would like to combine before I do any other movement. So I'm going to go ahead right here. 5x minus 7x is negative 2x. Remember, that's not the subtraction property of equality. I didn't manipulate both sides of the equation. I simply simplified. So there's still a plus 4 there, and this is all still here. Okay, I'm going to go ahead and try and isolate my x variables. I have negative 2x on this side, and I actually happen to have negative 2x on this side. I'm going to try and move this one over by adding 2x to both sides of the equation. So I'm going to go ahead and write plus 2x right here. I'm going to write plus 2x right here so I know what to combine. Negative 2x plus 2x is 0. And over here, negative 2x plus 2x, they combined to get 0x again. This is the second equation that this happened. What the heck why are my x's going away? Did we, when we wrote these questions, did we mess up? What happened? Let's go ahead and continue on and see what's happening. Negative 2x plus 2x is also 0. They canceled.'re gone. The x terms are no longer. What remains is a 3 on the left side and a 4 on the right side. 3 equals 4. What are we doing? What is this? I'm going to leave that for a moment and go on to the third problem. Part C, or problem C, 2 times 3x minus 2, the quantity, equals 2x plus 8. I'd like to distribute these first. There are other ways to do it, but I'm going to go ahead and distribute this one over here first. 2 multiplies with 3x to get 6x. 2 multiplies with negative 2 to get negative 4. Notice negative 2. And that equals 2x plus 8. Nothing can combine on that side. I have simplified. Now I'm able to do some maneuvering, just like the previous problems you saw. 2x is on this side. I'd like to move it over with that 6x and, just kind of get things moseying along. Subtract 2x from both sides because it's positive. That is the subtraction property of equality. 2x minus 2x is 0. and I have 6x minus 2x, which gives me a good old 4x. Remember what we did on the other one, all on one step? I'm going to go ahead and do that here just to save time. Negative 4 on this side that I would love to add over to get the constants on the other side of the equation. Negative 4 plus 4 is 0. And then 8 plus 4 on this side gives me 12. So I have 4x equals 12. Not much room, so I'm going to say if I divide both sides by 4, I get x equals 3. All right? Hey, I solved an equation there. By the way, number of solutions. 3 is a solution to this thing. It's not the number of the solution. It's how many solutions are there. There's one solution in problem C. Problems A and B are a little bit more peculiar. We didn't really solve for x because the x is canceled out. And this wasn't by accident. This was very intentional. But you're going to see that there's a different setup for one of the problems than for the other problem. I'll explain why. I don't really want to give a lot of examples, but I'll explain why that is so you know how to answer this. So let's take a look at part A. In the end, the x is canceled, and all that you have left is negative 15 equals negative 15. Or if you add 15 from both sides, 0 equals 0. You have something that says, well, I don't know what x equals, but I do know that no matter what I do to the left side, as long as I use properties of equality, it looks like it's going to equal the right side. 0 does equal 0. That's a true statement. Do I just say, that's true? Not really. But it is true. 0 equals 0, negative 15 is negative 15. What happened was the x's ended up becoming irrelevant in the situation in that no matter what I substituted for x, it looks like that those parts of those terms were always going to cancel each other out anyway. If I substitute 100 for x, this becomes 600 minus 600. They go away anyway. And what I have is something that is a true statement, which means it lends to a solution. Like, meaning that, like this lends to solutions. Something's true. So it seems that no matter what I substitute for x, the left side is always going to equal the right side. And notice that I said no matter what I substitute for x, I could substitute 100 or 0 or negative pi or 5/3. No matter what, it's going to give me a solution. So how many solutions are there? I could plug in 1 and 2 and 3. I can plug in anything. Any real number would work. Any imaginary number might work. There is an infinite number of solutions here. This is infinite. I'm going to go ahead and make that blue in a bit. There's an infinite number of solutions for this because no matter, and here's the reason, no matter what you substitute in for x in this equation, the left side ends up equaling the right side. And that's the goal. When you do x equals 3, that means no matter what that means when I substitute 3 into this equation, the left side will equal the right side. If I substitute 4 into this equation, the left side won't equal the right side. The whole goal is what values of x make the left side equal the right side, and here I can plug in anything, which means there's an infinite number of solutions. Problem B has a different story. This says 3 equals 4. That ain't true. We know that. 3 doesn't equal 4. But the x is eliminated kind of in the same way that the x is eliminated here. They're gone because it says no matter what I substitute for x, those parts of those terms are going to kind of void each other. They'll be gone and canceled out. So it looks like all that's left is this 3 and this 4. So it seems like no matter what I do, that left side isn't going to be equal to that right side. It seems like no matter what I substitute for x, I'm going to get this mistaken, non-true situation. Doesn't look like I can substitute anything for x to make this thing true if they cancel. So there are 0 real solutions in problem B. There are 0 solutions here. So check that out. No solution for B, 1 solution for C, and infinitely many solutions for A. And that's the setup there. So what do you look for? You look for, can I actually get a solution for x? Or if I can't because they cancel, does the left side equal the right side? If yes, an infinite number of solutions. Does the left side equal the right side? If no, 0 solutions. And for linear equations, those are the only 3 possibilities. Generally, we like to get the 1 solution case. Okay. All right, moving on. Number 13, solve for y. Solve for y means isolate y, and it means solve even if there are other variables in the way. I just want to get y by itself. Let's see what occurs when I do that. I'm going to go ahead and divide both sides by 4 because 4 is multiplying with y, so I'm using the division property of equality. So if I divide both sides by 4 like that, you get y equals 8x plus 20 over 4. And some people might say, hey, that answer is good. But to explore this a little bit deeper, because 8 can divide by 4, and because 20 can divide by 4, and because it's a common denominator, I'd love to instead actually split this here. I want to divide by 4 with every term because I can make this a little better looking than it started off. 8 divided by 4 is 2, and 8x divided by 4 is 2x. 20 divided by 4 is 5, so you're going to be left with y equals 2x plus 5. Although the answer like this works, because they can divide, this is better. It's better, it's encouraged, it's recommended, it's suggested. Let's go for that whenever we can. Number 14, solve for n. N is right up here in the numerator, multiplied by 3, added with k, all divided by p. Looks like I have at least 3 steps to do to get n by itself. Okay, now keep in mind, we're not finding an exact answer. We're solving in terms of some of the other variables. So here I'm not going to get like n equals 2. I'm going to get like n equals something with a k and a p in it. All right, p is dividing in the end, so let's go and start by multiplying both sides by p, because then p over p becomes 1. No more fraction mess. I now just have 3 times n plus k equals 5 times p. 2 more steps to go. K is adding with the n term, so I'm going to subtract k from both sides right here, like that. K minus k is subtraction property of equality. K minus k is 0, and I have 3n left on this side. 5p minus k cannot combine, so I'm just going to go ahead and leave them separate like that. 3 is multiplying with n. If I divide both sides by 3 now, then I'm going to go ahead and get, remember, whole thing divides by 3. And notice the difference here. I did divide everything by 4 here, but I split it because I could divide it. Here, 5 can't divide by 3. K can't really divide by 3, so I'm going to go ahead and leave that all as one big fraction this time. I'm going to have n equals 5p minus k, all divided by 3. That's the best looking answer I think we can write for that one. I'm going to go ahead and say that. Okay, n is by itself. I have solved for n. Number 15, solve for y. Here's the y term. There's the x term in front. Let's go ahead and move it over. Now keep in mind, 9x is adding with negative 2y. You see the subtraction, but 9x is positive. So I'm going to subtract the 9x over to the other side. Let's use a different color. Minus 9x, subtraction property of equality. Don't forget this negative here. This is key. That's a negative 2y that still exists on this side of the equation. So I have negative 2y equals, I'm going to write the negative 9x first, negative 9x plus 18. Note that the 18 is positive. I got to get y by itself now, and there's a negative 2 that multiplies in front. Division property of equality. Let's divide by negative 2. Divide by negative 2 and divide by negative 2. Now, negative 2 cannot divide into both of these, but because we're going to deal with slope-intercept form stuff later, this is what's called standard form of a linear equation. Even if you don't know that yet, that's fine. And if I go ahead and divide all these by negative 2 like this, you're going to get what's called slope-intercept form. Y equals mx plus b, if you've heard that before. Slope-intercept form of a linear equation. Negative 2 over negative 2 is negative, or positive 1, so I get positive y, good, equals negative 9 over negative 2 can change to positive 9 over positive 2. And I'm going to leave it as a fraction. This is, again, for slope-intercept form, fractions are the nice way to go about this. It can't reduce. I'll leave it like that. If you write 4.5, it's fine. But I'm going to leave it as 9 over 2. 18 divided by negative 2 is negative 9. So when you add a negative 9, that becomes subtraction. Y equals 9 halves x minus 9. And that's the best looking answer for algebra's sake. That is slope-intercept form for that one. Not that you need to know that, but we got y by itself. Okay. All right. We got 2 inequalities here. We are going to solve them and graph the solution on the number line. Solving inequalities is just like solving equations. Treat the symbol that's in the middle like a form of balance that separates the two expressions, use properties of equality for both sides to keep the balance in, even if it's an inequality here. So when I want to get x by itself, -7, 7's being subtracted here, let's go ahead and add 7 to both sides of the inequality for the same effect that we would be doing with equations. Now I have 2x is greater than or equal to 8. So I'm going to maintain this greater than or equal to here unless you multiply or divide by a negative number. I assume that's going to pop up in probably the next question. 2 times a number is greater than or equal to 8. So what must that number at least have to be to make this true? Let's divide both sides by 2 and figure that out. Okay, 2 divided by 2 is 1. So we go ahead and get x is greater than or equal to 4. What this means in a trickle-up scenario, if 2 times a number is greater than or equal to 8, x must be a number that is 4 or greater. If x is 4, 8 is equal to 8. If x is 10, 2 times 10 is 20. That's greater than 8, so that works. So that's kind of what we're going for. Or if I substitute 10 into here, it makes the statement true. That's all we're going for. So x is greater than or equal to 4 is the solution to the inequality. That means any number that is greater than 4 or 4 itself works. So how do you graph it? We have a number line here. Well, here's the number 4 itself. X can be 4, so I'm going to go ahead and I'm going to fill in that circle right there. Close circle. And if x can be anything greater than 4 as well, I'm just going to go ahead and draw an arrow that goes this way. And these are all the values of x that can be represented there. If x is anything less than 4, it's a problem. It doesn't give us a true statement up there. There it is. Okay, number 17. 2x plus 4 is less than 5x plus 6. Let's solve. Now, I'm going to provide you ideas. There has to be a little bit of a why here because I don't want you to make mistakes. There are 2 different ways you can go and solve this, and both of them can cause hiccups. Let's be careful either way. I'll provide you forms of incorrect portions, and they're going to be drawn in red when I do. Okay? So the first one I'm going to go ahead and do in green. I'm going to go ahead in one of these scenarios, and I'm going to subtract 5x to both sides so I can get my x term to the left side of the inequality. 5x minus 5x is 0, so that's gone. 2x minus 5x is negative 3x. So here I have negative 3x, and this plus 4, I'm going to keep plus 4 here for a moment. Plus 4 is less than, notice it's still less than, 16. Okay? If I subtract 4 on both sides, I'm going to get negative 3x is less than 16 minus 4 is 12. Now, if I divide both sides by negative 3, just because I'm running out of room, if I divide both sides by negative 3, here I have x. 12 divided by negative 3 is negative 4, and here I have a, it's in red, less than. So I have x is less than negative 4. Now, I'm sure you already know the mistake because I talked about it for number 16, and because it's in red, I think you know what's going to happen. But I'm still noting it for good reason. Okay, that's one way we can go about attempting the problem. Here's another way we can go about attempting the problem that you have to be careful of. I'm going to do it in purple. So instead of subtracting 5x to the left side to have this over here, what if I wanted to make the x term positive? What if I subtracted 2x from both sides instead and said, all right, here I'm going to have a positive 3x on the right side of the inequality. So here I have a 4, and that's less than 5x minus 2x is 3x plus 16. Okay? So if I subtract 16 from both sides to get this by itself, 4 minus 16 is negative 12. It's the opposite of 16 minus 4. So negative 12 is less than 3x. And here, if I divide 3 from both sides, I'm going to have, negative 4? Negative 4 is less than x. Now, I didn't write anything in red here. But you know that there's an incorrect thing here, so let's play off this one for a moment. Let's say that I did this and say, I want to graph it, right? Graph on a number line. Negative 4 is less than x. Here's what a lot of my students have done in the past. Negative 4 is your boundary point. So we're going to go ahead and place a circle on negative 4 because it's not equal to, it's going to be an open circle. I'm sorry, I shouldn't put that in red. That should be in purple. That part's correct. Now, I see a less than symbol right here, and we think of less than as going to the left. So I'm going to go ahead and, in nice big red, draw it to the left and say, here are my x values. Now, there's a mistake. And the mistake has everything to do with the fact that you're reading this as less than. Why do we read it as less than? Because we read our values from left to right. -4 is less than x. There's nothing wrong with saying that. The problem is taking that less than and thinking about the fact that it's the x's that are less than -4. See, x isn't less than -4. If I read this right to left, x is greater than -4, not less than. So the problem with this is the way that it's written. I suggest for my students, and that's why I did this first, I suggest for my students to write this so that the variable is on the left side of the inequality. So if you want to do that, you can swap this around and put the x on the left side as long as you flip the inequality with it. Have this alligator mouth, whatever, I forget what they call it, have the mouth eat x every time. So I'm going to rewrite it as x is greater than -4. That's the correct way to write that version of that inequality. So it shouldn't go to the left, it should go to the right. X is greater than -4. Now look, you can try and substitute numbers to see if your thing works. You can even try it for your original inequality. For the sake of time, I'm not going to do that. But this is the true statement here. So what happened with this one? Well, you have to remember, what we actually did here before this was we divided both sides by a negative number. And when you divide or multiply by a negative in an inequality, the inequality flips. Why? There are many reasons, but you can see clearly that it should be this way anyway. So accepting of the fact that works. So which way should you do it? If you have a statement that has this stuff, which way should you go about trying to solve the inequality? Would you rather have positive variables in the end, only to flip everything over afterward? Or would you rather have negative variables on the left side, provided that you got to flip over once you divide by the negative? That's your choice. I just presented you with both options. There they are. I'm done. All right, let's go ahead and move on. Number 18. The following equivalent equations were written to solve the given equation. Write the property from the term bank that guarantees that each equation is equivalent. Okay, we're trying to say what happens from this step into this step to make things so. And if you want, you can write in between steps. I'll probably do it with you as well, so it helps explain what was the action to describe an A from step 1 to step 2. So from step 1 to step 2, it looks like they did a little bit of simplification. It looks like they went ahead and distributed the 3 into the x and the 2, so it gives you 3x plus 6, 3 times 2. So it looks like they used the distributive property here. This one was the distributive property of equality. Of equality, I shouldn't say that. That's totally wrong. They used the distributive property here. This equation was given, by the way. The reason why this is because they told you it was. Okay, what happened next? So it looks like their action removes the x's over here, and it looks like this 5x reduced into a 2x. That can only happen if you subtract 3x from it. So it looks like what they're doing is they're subtracting 3x from this side, and of course, for balance purposes, they did it from this side. They subtracted 3x because it was a positive. So it looks like we're using the subtraction property of equality for part B. I'm going to put property of equality. All right. For the next thing, I was looking at, oh wait, we just did that. For the next thing, from this step to this step, it looks like the -8 was moved over. We've done these steps already together a lot, so I'm not going to beat a dead horse. Looks like they're adding 8 to both sides here. Keeps balance. That's for equality purposes. That's using the addition property of equality. Addition property of equality. And the last stage, we go from 2x to x, or from 2x to 1x, right? So we are going to be dividing both sides by 2 in order to obtain that 1 right here. And of course, 14 turns to 7 for the same reason we divide by 2. And that is the division property of equality. Division property of equality. That is, I'm just going to point to it because you might think distribution property of equality, which doesn't exist. It's just distributive property. So that's just it right there. We never combined like terms here. The reflexive property is not one that we should be paying attention to right now for algebraic purposes. It's nothing you'll really know. The symmetric property, just so you're aware of what it is, I actually used it once. Where did I use it? I used it right here. What I did was I flipped, whoops, I'm covering it with my face. I flipped the inequality here. The other time that I used it was way back, let me find it, right here. This is the symmetric property of equality. I mirrored my equation and wrote it this way. I flipped them. That's the symmetric property of equality right there. But we didn't use it right here. All right, that's the end of that page. I have one more page to go. Let's get there. Melanie and Josiah both started with the same equation, however, each of them solved it differently. That's allowed. The first step each student made is shown. Use a property to describe what each person did and why it was a reasonable method to choose. Okay, it looks like Melanie is distributing here, just like the previous problem we did. She properly distributed the 2 into the x and the 3 to get 2x plus 6. Property used, distributive property. I'm just going to write distributive. This could be a good choice because what? I'm just going to talk about it. I'm not going to write it, so just hear me out as I say it. Why is distributive property okay here? Because your whole goal is to get x by itself, and x is inside this quantity of parentheses. And it would be nice if we got it outside of it for simplification purposes. Look at what steps you would want to do next when it comes to solving. It looks like I could subtract the 6 and divide by 2. I couldn't do that when it was inside parentheses. I can't just say, hey, let's minus 3. Because 3 is protected by this parentheses business right here. 3 is really not a 3. It's really a 6. Because it's multiplying by 2. This isn't allowed. I can't do this minus 3 thing. I can only do it if I first distribute. If I simplify, then I can do the subtraction here. Minus 6. And then divide by 2. So it's a good plan because for simplification purposes, I now have an x term by itself, and I can start moving other terms over. That's a good way of making it happen. Now what did Josiah do? The 2 went away here. I don't have 2x plus 6. The 2 is gone. And this 14 looks like it reduced to a 7. Where'd it go? Well, 2 is multiplying by this quantity by here, right here. It looks like he divided both sides by 2, because 14 over 7 is 2, and 2 over 2 is 1. And what is 1 times the quantity x plus 3? Well, it's just x plus 3. So that all went away. Now, before I said there was another problem I could have done this with, I don't know where it was, but it was something I was going to do with it. You could have divided both sides by 2. Is this always a recommended practice? No, it depends on whether you can notice that it's available and whether you can divide by something and still get an integer. But it's a nice one because your numbers get smaller. So what did we use? We divided both sides by 2. That's the division property of equality. Now, why is this a good choice? Well, the same reason as the last one, it's a good choice because you have the x term outside of a quantity, and you can just do a couple more steps, actually one more step to make this solved. The really cool thing that Josiah was able to do, though, was, again, reduce a step and make your numbers smaller. So, and also it practices different things. So, could be a good choice. Which one do you prefer? I think most prefer this one because they've seen it and done it more. And it can be used every time, whereas this time, I wouldn't use this if it gave me a fraction right here. If I had to divide by 3, I wouldn't be doing it. Even like myself, I wouldn't recommend you do it either. All right, a few more problems here. Number 20. For the expression above, where? Okay, right here. For the expression above, 11 minus 3 squared, what is the exponent? I'm just going to give you the answer. The exponent's 2, the thing you're raising the power to. For the expression above, what is the base for the exponent? Now, the answer is 3. Okay? Now, I want to let you know, some people might think, well, hang on, you've been talking about negative 3 so many times here. Yeah, but 3 is the thing that's being squared. If we use order of operations, I square something first, and then I subtract afterward. I shouldn't have circled, I should put in parentheses. You square something first, and then you subtract afterward. Negative 3 isn't being squared, just the 3. So 3 is the base for this guy that's happening right here. It's like if I had parentheses right there. I'm not squaring a negative 3, I'm just squaring the 3. Evaluate the expression above. Okay, well, just like I said, let's square the 3 first, and then let's rewrite that. 3 squared is 3 times 3, so that turns into 9. We're doing 11 minus 9, and 11 minus 9 is 2. Okay, I'm done. Evaluate, losing my voice, evaluate for x equals 4. That means come up with this thing if we substitute 4 for x. there's a motto that I say for my classes, and they already probably know how to repeat it right now. When in doubt, use your damn parentheses. And I use that word for emphasis. What I mean is, if you're unsure as to whether or not there should be parentheses around the 4 that I substitute, use them. Like right here, 4 substitutes for x, I'm going to use parentheses around it. Right here, 4 substitutes for x, I'm going to use parentheses around it. This allows you to use order of operations properly when you do, and it allows you to go ahead and when you need to, goes ahead and lets you know that this is multiplication that's happening here. Okay. 3 times 4 squared. I don't multiply 3 with 4 first because exponentiation comes before multiplication. I'm going to do 4 squared first. So this becomes 4 squared, which is 16. I'm going to go ahead and multiply these ones right now because I'm able to. 5 times 4 is 20, so I'm going to be subtracting 20. And there's a plus 2. 3 times 16 is 48. Now do not do 20 plus 2 right here because this 20 is negative. You may do negative 20 plus 2, but I'm just going to go ahead and do it in order. I'm going to go do 48 minus 20 first. I think that's easier too. It makes less mistakes. 48 minus 20 is 28, and plus 2, that gives me 30. I'm going to use a different color there. That's a little too much blindness when you only see one color. All right, number 24, evaluate 5 plus 2 times the quantity, 1 plus 3, which gets squared. Order of operations, parentheses actually comes first. The grouping for which which is being added should happen first. I'm going to do 1 plus 3 before anything else. Notice I do not do 5 plus 2 right here because 2 is multiplying with this quantity. You can't just turn it into 7. So 5 plus 2 shall remain. I'm going to do 1 plus 3, which becomes 4. And just like the previous problem, I will square the 4 before I multiply by 2. And you might wonder if there's a difference in answers. Almost always yes. 2 times 4 is 8, and 8 squared is 64. 4 squared is 16, and 2 times 16 is 32. 64 and 32, not the same number. So 5 plus 32 gives me 37. That is a 7. There we go. Okay. Number 25, evaluate. I have this grouping on top, 2 times 5 squared. And then on bottom, I have 3 plus 5 minus 2 plus 4. Now, there aren't parentheses here, but there are groupings. The numerator, we simplify together. The denominator, we simplify together because of the way that the large bar is expressed. It's like there are parentheses here and here, but we don't need them. All right? So let's go and simplify top and bottom separately. 5 squared happens first. That becomes 25. So the 2 is right here, which multiplies by 25. 3 plus 5 is 8. Minus 2 is 6. Plus 4 is 10. So I'm just going to go ahead and do that right now. 2 times 25 is 50. Divided by 10 gives us 5. All right. Because I already passed my hour mark, you can tell I'm going a lot faster here. I got 5 more problems. They're not too bad. They seem more like the basic review things, and we did harder problems before it. All right, so number 26, simplify. By simplification means that, I think I already said this, you distribute everything out. There should be no parentheses in the end of what you have. Nothing factored, anything like that. Distribute all of it out and combine like terms. Those are going to be our simplification rules for you. Okay? So there are parentheses here. I love to distribute this. 2 goes into the x, 2 goes into the negative 2. I'm also going to distribute this negative into these items here. It's almost like a negative 1 is multiplying with 5x and a negative 1 is multiplying by 7. You know, if the number's not there, it's implied that, that it's a 1. So distributing the negative to me kind of just means change the signs, but you got to change it for both of them, not just the 5x. Okay? So 2 times x is 2x. 2 times negative 2 is negative 4. 2x minus 4. Right here, the negative distributes into the positive 5x and the positive 7. So that'll give me a negative 5x and a negative 7. When I combine like terms, I have 2x minus 5x. And that gives me negative 3x. And I have negative 4 minus 7. They're both negative, so we go further negative, larger number. It's like 4 plus 7, but negative. That's a minus 11. Negative 3x minus 11 is simplified. There is nothing to solve for. You're not going to try and solve for x. You're just simplifying an expression. It's not an equation. Number 27, 6 plus 3 times the quantity, 2x minus 5. Whoops, I wanted to use green. I shall distribute the 3 into the 2x and the negative 5 right here. 6 hangs out on the outside as I distribute. 3 times 2x is 6x. 3 times negative 5 is negative 15. And I'm almost done. I must now combine like terms. The 6x can't combine with anything. I'm just going to go ahead and leave it there. 6x minus 15 gives me negative 9. I think we had 6 minus 15 before. So I'm just going to go ahead and tell you that it's that. 6x minus 9 is the simplified version. We're done with that. Number 28, 9 minus the quantity 2x minus 6. Just like before, distribute the negative into these two things. Just be careful here because now we're going to subtract a negative right there. So the signs change with the terms. If all the signs were positive, they become negative. But if you have any negative terms in there, they become positive. Minus 2x here, but now this is minus negative 6. So that becomes plus 6. That one turns positive. It was negative, it's now positive because you're subtracting it. Same thing as before, negative 2x doesn't combine with anything, so I'm just going to leave that there. And 9 plus 6 becomes 15. You might ask, does it matter which order they're written in? For the sake of the simplification stuff, no. I'm writing these in what's called standard form. I'm getting the x term first and the constant second. If you wrote 15 minus 2x, you're correct. Nothing wrong with it. If they ask for standard form, it's a different story. You're not being asked that, but either works. And last two, we already graphed these inequalities with solving something, so I'm just going to go and graph these very fast. X is less than negative 3. That is an open circle on the boundary point of negative 3, and any value that is less than will apply. So I'm going to draw the arrow to the left, as you can let any x value there go. And finally, number 30, x is less than or equal to negative 3. Same arrow, same boundary point, but your circle is now closed because negative 3 can be included within this answer. All right, that is your practice test. I spent just a hair over an hour to make sure to talk about that. There were 30 problems. It's about 2 minutes a problem on average. Some problems were longer, some were shorter. Hopefully that all panned out though, and you learned things along the way, and you can apply it when it comes to your actual test, which should, it should kind of reflect the things that we just learned right here. So you get these practices in, you can make sense of how to explain situations, use properties of equality, double check your work. I think you'll be pretty balanced here. So I hope that you enjoyed this video, guys. Ask me questions in the comments if you have any, or ask your teacher. If you have me, ask me. But this is some good review for you. Obviously, it's best that you practice these first, and then you only go to the problems that you didn't make sense of. And obviously, now that you're watching this point, you already did all that. So thanks for watching this one. I'll make sure to try and do solution guide videos for all practice tests that we have leading up to another test. And if you're watching from the outside looking in, you can try it with the PDF in the same way. Let me know if you have questions as well. My name is Mr. Robinson. Have a good day.